Alright, in this video we're going to talk about the enthalpies involved in phase changes, and then combine that with heat capacities and talk about heating and cooling curves. Alright, the first thing I want to do is talk about some terminology involved in phase changes. Now, a lot of these terms you're probably going to be familiar with, but there may be some that you've not seen before. So when we go from a solid to a liquid, of course in our everyday language we would say that that's melting. And we use that term in chemistry as well, but actually there's another term that you'll sometimes see, and that is this process is sometimes called fusion. And we most often see that when we're talking about enthalpies. So they probably won't call it the enthalpy of melting, they'll probably call it the enthalpy of fusion. Now going the other way, I don't have a fancy term that we often use, that would just be freezing. When we go from a liquid to a gas, that's evaporation, or you might see the term vaporization. Going the other way from a gas to a liquid, we would call that condensation. And then going from a solid to a gas, sometimes this term is a little bit less familiar, but that is called sublimation. And then going in the other direction, from a gas directly to a solid, is called deposition. Now, for all of our phase changes, there is an enthalpy associated with them. And when we're going in this direction, so when I'm going from a solid to a liquid, or a liquid to a gas, or a solid to a gas, all of those processes are endothermic. Right, we have to put energy in to make that happen. Right, think about boiling water, converting water from a liquid to a gas. We have to heat that on our stove. Right, we have to put energy in order to make that happen. So it should make sense that that is an endothermic process. So then that means that going in the other direction, going from a gas to a liquid, or a liquid to a solid, or a gas to a solid, all of those processes are exothermic. Right, they're giving off heat when you go in that direction. And another way in that the enthalpies of phase changes are related is that if I'm going from a liquid to a gas, or a gas to a liquid, and then the other opposite phase change, this applies as well, the magnitude of the enthalpy involved is the same. It's just the signs that are different. So when I'm going from a liquid to a gas, and so I have vaporization, that's going to be an endothermic process. So if the delta H of vaporization of water is positive 44.01 kilojoules per mole, then going in the other direction, condensation, so going from H2O gas to H2O liquid, the delta H of condensation is negative 44.01 kilojoules per mole. And so that's true about the relationship between vaporization and condensation. The same thing is true about freezing and melting, and the same thing is true about sublimation and deposition. The magnitudes of the enthalpies are the same, it's just the signs are different. So, as an example problem, if we wanted to calculate the amount of heat needed to vaporize 90 grams of benzene at its boiling point, so what we have is we're boiling benzene, so it's going from a liquid, C6H6 liquid, to C6H6 gas. So this process is vaporization, so I can write that as a thermochemical equation just like we did in earlier videos. And so I can say that the delta H for that process is 30.8 kilojoules per mole. And so this really is just like a stoichiometry problem with enthalpy. Just the type of reaction we happen to be looking at is a phase change. So the molar ratio is simply 1 mole to 1 mole. And so that, since it's even easier than a lot of the other stoichiometry problems we did with enthalpies, fundamentally it works the same way. I've got to get my 90 grams into moles, and then I can use the enthalpy of vaporization in that 1 mole of C6H6 liquid requires 30.8 kilojoules in order to vaporize. And they were helpful enough to give us the molar mass of benzene. I don't even need to calculate that. So to solve this problem, I would just take my 90 grams of benzene, and then 1 mole of benzene requires 30.8 kilojoules in order to vaporize. And so the delta H for that process is 35.5 kilojoules. All right, the next thing I want to talk about is heating curves. And so what this graph represents is the heat required to take ice, in this case at negative 25 degrees Celsius, to steam at 125 degrees Celsius. And so the temperature is on my y-axis, and on the x-axis I have the amount of heat required for each of these processes. And so there are a number of different steps involved in getting from solid ice to water vapor. And you notice that the graph is kind of stepwise, right? So I think it probably makes sense that in order to take ice from minus 25 degrees Celsius to 0 degrees Celsius, I have to heat that up. And so as I move along the x-axis and I add heat to the ice, the temperature increases until I get to the melting point. Now it turns out that I can't increase the temperature of the ice until I've melted it all. And it takes heat to melt the ice even when it's at 0 degrees Celsius. And so the reason we leveled off is because we've now got the ice at 0 degrees Celsius, but then we have to put in additional heat to cause it to melt. And so the temperature doesn't change as we continue to add heat until all of the ice is melted. At that point, I now have liquid water at 0 degrees Celsius, and so when I continue to add heat to that, the temperature will go up until I get to the boiling point. Right? And once I get to the boiling point, the temperature again won't change because now all the heat that I'm putting in is going into vaporizing the water. Right? And this should be familiar to you if you do any cooking. Right? Part of the reason we use boiling water to cook things is because it keeps the temperature constant. As long as the water is boiling, it's at 100 degrees Celsius, and so it makes for consistency in our recipes. And so the temperature won't change until I've converted all of the liquid water into steam. And so it takes a lot of energy to vaporize water, and so we're vaporizing the water, we're vaporizing the water, we're vaporizing the water, we're vaporizing the water, until I get to this point, and now all of the liquid water has been converted into steam, and so now when I add the heat, the temperature goes to increase again. And so if we wanted to calculate the total heat or the enthalpy for this entire process, it would involve a number of steps. So temperature changes, we would use Q is equal to MC delta T. And so each of the parts of the curve where I'm just changing the temperature, we would use Q is equal to MC delta T. But we have to be careful because the heat capacities of ice, liquid water, and water vapor are not the same. So that would have to be 3 separate calculations using Q is equal to MC delta T, in this case using the correct heat capacity for whether I have the solid, the liquid, or the gas. And then for these parts of the curve, to calculate those heats or enthalpies, I would need to use the problem that we just did, and I need to use the enthalpies of phase changes. And so to get the heat for those processes, I would take the moles of the substance times the delta H of that phase change. All right, so let's see what one of these problems would look like and how we would go about attacking that. All right, so let's take a look at an example problem. So I want to know how much heat is given off when 15 grams of liquid water at 50 degrees Celsius is converted to ice at minus 25 degrees Celsius. And so what I often like to do is to make one of my heating and cooling curves to kind of diagram out what's going on. And I'm going to go to temperatures I don't need and then sort of zoom in on what I'm actually doing here. So I'm going to make my heating curve from minus 50 to 150 degrees Celsius. And then relevant temperatures to us are 0 degrees Celsius, the freezing point of water, and 100 degrees Celsius, the boiling point of water. And so sort of the full heating curve for this would be, all right, I need to heat the ice to the melting point, then melt it, then heat the water to the boiling point, then boil it, and then heat the steam. Right? Now I'm not actually doing all of these things in this example. Right? I'm going from, let me change the color here real quick. Here we go. So I'm going from negative 25 degrees Celsius and 50 degrees Celsius. Right, and I probably should have, right, the sig figs are going to be messed up. So let's change the problem here a little bit. So we'll go from 50.0 to 25.0, or to negative 25.0, so that our sig figs are a little bit better, right? So I'm focused on three parts. I need to cool the liquid water to the freezing point, then I need to freeze it, and then I need to cool the ice from 0 degrees to 25 degrees. So this is going to be a three-step problem. So step one, I'm going to cool the water. And so to calculate the heat given off in that process, I'm going to call this Q1 is going to be MC delta T. Then for the freezing itself, I'm going to need, I'll call that Q2. I'm going to need to use N times delta H of freezing. So I'm going to take the moles of water and multiply that by the enthalpy of freezing. And then finally, I need to cool the ice. And so that's back to using Q is equal to MC delta T. All right, so when we now attack the problem, let's get Q1 first. So I need to see how much heat is required to cool the water from 50 degrees Celsius to 0 degrees Celsius. So for that process, I'm going to use MC delta T. So Q1, I've got 15 grams. I need to be sure I use the correct heat capacity. So I need to use the heat capacity for liquid water. So that's 4.18 joules per gram times degrees Celsius times the change in temperature. Remember, it's always the final minus the initial. So I'm going from 50 to 0. So final is 0 minus 50. So my grams cancel, my degrees Celsius cancels, and so my units are going to be in joules, and it's going to be negative. And that makes sense. When I'm cooling it, it's giving off heat. So Q1 is going to be negative 3140 joules. All right, let's attack Q2. So I'm going to erase this work for Q1 to give us some space to work on. All right, for Q2, I need the moles of water, and I need to multiply that by the enthalpy of freezing. So first let's get the moles. So I have 15 grams. The molar mass of water is 18.02 grams per mole. And so I have 0.832 moles of water. And now we also need to be careful. They've given me the enthalpy of fusion, right? So they've given me the enthalpy for melting, and I'm going in the other direction. So it's not a big deal. I just have to be aware of the sign, right? The delta H of fusion is positive. The delta H of freezing is the same numerical value, but it's going to be negative. And so my Q2 I get 5.01, and I'll be careful of the units. This is in kilojoules. And, I'm sorry, the 6.02 should have been times a negative 6.02, because my Q2 is going to be negative 5.01 kilojoules. And so back to the units, right, when I use the Q is equal to mc delta T, my heat comes out to be in joules. When I use the enthalpy of a phase change, if it's given to me in kilojoules per mole, then the Q for that process is going to be in kilojoules. And I need to be consistent on the units. Now I could convert everything to kilojoules or everything to joules, whatever you prefer, but since two of them are going to come out to be in joules and one of them is going to be in kilojoules, I think the easiest thing to do is to get this into joules. And so kilojoules to joules, I need to multiply by 1,000, and so I have negative 5,010 kilojoules. All right, so my Q2 is negative. No, I'm sorry, I misspoke there. Not kilojoules, I converted it to joules. Okay, so we have one piece left. We need to get Q3. So again, I'm going to erase some of this to give us some more room. All right, so now Q3, we're back to using mc delta T. And be sure I use the correct heat capacity. Now I need to use the heat capacity for ice. And then for the temperature, again, it's the final minus the initial. So it's minus 25 minus 0. And again, the grams cancel, the degrees Celsius cancel, and my heat for this step will be in joules. And when I multiply all that out, I get negative 784 joules. And now if you notice, all of the signs were negative, right? So when I'm going in this direction, when I'm cooling, that's always going to be the case. All of those steps will be exothermic. If I was going in the other direction, all of the Q's would have been positive. So they always have to have the same sign. I shouldn't get some positive and some negative. If you do, something has gone wrong. When we're going in this direction, they should all be negative. And so to finish this problem, I just need to add up the 3 Q's from these different steps. And so I'm going to call that the total heat is going to be negative 3140 minus 5010 minus 784. And because I only know those first two to the tens place, I need to report my answer as negative 8930 joules. All right, so if you want to see another example of one of these, I do have another video with a similar problem.